What's up everyone, welcome back. Patrick here, and moving on to another example, another trig limit we're going to deal with. So we got the limit as x approaches 0 of sine mx over sine nx, where m and n are just some kind of real number, just some kind of constant. And like I did in the previous examples, I'm going to be using these results that we've talked about in the previous examples to help us out throughout the process. So if you didn't watch the previous examples, the other trig limits that are listed on the site in order before this one, highly recommend you watch those because lots of concepts carry over to whatever current example we are on. So the limit as x approaches 0 of sine mx over sine nx. Now the first thing I'm going to do here is I'm actually going to split these up into two separate expressions. Notice it's one expression now, but we can rewrite this as sine mx times 1 over sine nx, like that. Okay, so I took this one expression, split it up into these two separate expressions. And now what we can do is we can actually create two limits, because from limit laws, if you remember, if we have the limit as x approaches a of f of x times g of x, two functions that are multiplying by each other, we can rewrite that as the limit as x approaches a of f of x times the limit as x approaches a of g of x. Right? That's one of the limit laws that we've covered. So that's what I'm going to apply here. So we're going to have the limit as x approaches 0 of sine mx, like that, times the limit as x approaches 0 of 1 over sine nx, like that. So I took this limit here and I split it up into two separate limits. And now what I'm going to do is I'm going to deal with both of these limits separately. So first off, I'm going to rewrite this one up here. So we got the limit as x approaches 0 of sine mx. So I'm going to see what I can simplify this bracket to. Now, what I can do here is I can actually multiply this by mx over mx. So it's like I'll be multiplying it by 1. And so notice what we'll get here. We'll get the limit as x approaches 0 of, let's combine these two. We'll have sine mx over mx times this mx that's remaining in the numerator. Right? So I kind of just took this mx in the denominator and put it under this sine mx, and then this mx still remaining in the numerator. So now I can actually apply that limit law again, and I can split these up. So I'll have the limit as x approaches 0 of sine mx over mx, like that, times the limit as x approaches 0 of just mx. Right? So I took this limit, split it up into two separate limits. Now notice here, this is in this format. It's actually in this format as well, where this m and this n are just equal. So this, if we look at this, we got m, and instead of this n, we have another m. It's just going to end up equaling m over m, right? This constant over this constant, which is just going to equal 1. But if you want to show it with a little bit more work, we can use this result. We could do a change of variables. So we could let theta equal mx. Let's actually do it on the side here. And so as x approaches 0, that means theta is going to be approaching 0 as well. As this x approaches 0, m times 0 is 0, so that means this theta is going to be approaching 0 as well. So we can do a change of variable here, we can have the limit as theta approaches 0 of sine theta over theta, right? mx, we let that equal theta. And we know that this is equal to 1. Okay, so what we did, this bracket is 1. And so we simplified this bracket. Remember, this is what we started with. We're doing it up here. We simplified the limit as x approaches 0 sine mx to just this limit. The limit as x approaches 0 of mx. Right? So using that result here, basically this bracket is going to equal the limit as x approaches 0 of mx. Right? Took this, simplified it to here using that work, and then this other limit stays as is. We haven't touched that limit yet, so we got the limit as x approaches 0 of 1 over sine nx, like that. So now what I'm going to do is I'm actually going to work with this limit, see what we could simplify this bracket to. So I'm going to do the same thing. I'm going to do it up here. Let's actually split this up just so we're not getting confused. So we got the limit as x approaches 0 of 1 over sine nx. Now this one's going to be a little bit more unique, but the process is going to be very similar to what we did here. Remember, this sine mx we multiplied by mx over mx. So we're going to take this 1 over sine nx and same thing, multiply it by nx over nx, which is like multiplying it by 1. So we're keeping that expression the same, we're just adding more to it. And now what I'm going to do is I'm going to take this nx in this numerator and put it for this numerator here over this sine nx. So I'm going to rewrite this as the limit as x approaches 0 of nx over sine nx, like that. That's going to be one expression multiplied. Notice that this nx is still remaining in the denominator, so I'm going to write this as 1 over nx. Right, so this and this are the same thing. I just basically just switched this 1 and this nx. And you can do that because we're multiplying here. So now here's where stuff gets a little unique. So we could apply that limit law, so I'm going to do limit as x approaches 0 of nx over sine nx. Split up these limits. So we got one limit here, and then we're going to have limit as x approaches 0 of 1 over nx, like that. So this is where it's going to get a little bit interesting. Here, working with this limit, I'm actually going to do a change of variable at this point. So I'm going to let theta equal, actually, you know what? We already used theta for the mx. So you're not getting confused. Let's use another variable. Let's say a, capital A. So we're going to say a is equal to nx, like that. We're introducing a new variable. So as x approaches 0, that's the same as a approaching 0 as well. As this x value approaches 0, this a value is going to approach 0. So we're going to rewrite this limit here as the limit as a approaches 0 of a over sine a, like that. So now I'm just working with this bracket on the side here. So notice that this is almost in this format, but it's not really, because over here we have limit as theta approaches 0 of sine theta over theta equals 1. Or if we're using a, we know that the limit, if I sub in a for this theta, we know the limit as a approaches 0 of sine a over a is equal to 1. But notice this is not sine a over a, it's a over sine a. However, what we can do, so this is where it's a little unique, we can actually rewrite this expression as 1 over sine a over a. Okay, because in general, if we have a fraction, let's say we have a fraction b over c. That's the exact same as 1 over c over b. Right? 1 divided by a fraction, so let's say we take 1 divided by 4 over 5. That's the same as like 1 over 1, this 1 is like over 1, times 5 over 4, multiplied by the reciprocal of that fraction, which ends up being 5 over 4. So 1 over 4 over 5 is equal to 5 over 4. So 1 over c over b is equal to b over c, or vice versa. b over c is the same as 1 over c over b. So we're just applying this here, right? This b over c, 1 over c over b, right? Just change this to be that. They're the exact same thing. And now notice, what can we do? Well, we can apply a limit law here because whenever we have the limit as x approaches a, going back to limit laws now, of f of x over g of x, like that, we can distribute that limit to the numerator and the denominator. So we can rewrite this as the limit as a approaches 0 of 1, this numerator, over the limit as a approaches 0 of sine a over a, like that. Okay, now the limit as x approaches a, going back to limit laws, of a constant, some kind of constant, like this 1 here, what's that equal to? That's just equal to the constant all the time. So the limit as a approaches 0 of a constant, using that limit law, well, that's just going to be that constant, which is 1. And then the limit as a approaches 0 of sine a over a, that's this law here, which I rewrote over here, which is 1 as well. And so this is just equal to 1. This entire bracket ends up equaling 1, and we showed it with this work here with the change of variable, and then we had to use a couple of limit laws. Right? So that's another result that you may want to keep in mind. This is how you prove it here. When you have the limit as theta approaches 0 of sine theta over theta equals 1, well, also the limit as theta approaches 0 of theta over sine theta is also equal to 1. Right? So you could flip these, and to show that work, you can just follow these steps here. Right? So this bracket here simplified to 1. So what do we end up with? Going back to what we're simplifying, remember, we're simplifying 1 over sine nx. This bracket here ended up equaling 1. And then we're just left with this limit here as x approaches 0 of 1 over nx. And I'm actually just going to leave that for now. So this bracket simplifies to this bracket here. So rewriting these, we got the limit as x approaches 0 of mx, right, what we simplified before, multiplied by the limit as x approaches 0 of 1 over nx. Took this bracket, simplified it to this using all of that work. And now what I'm going to do is I'm going to work with these two limits here, and I'm actually going to bring back that limit law where we have two functions that are multiplying by each other. Remember how we could split up the limit, right? The limit as x approaches a of f of x and the limit as x approaches a of g of x. Well, now what I'm going to do with these is I'm actually going to go this way. I'm going to go backwards now. Because notice that this here is in this format. We got x approaching a, x approaching a, x approaching 0, x approaching 0. And then this f of x is like this mx, and then this g of x is like this 1 over nx. So I'm going to use that limit law again, but I'm going to go the other way. Usually we're going this way. Now I'm going to be going the other way. So I can rewrite this now as the limit as x approaches 0, and then I'm going to be multiplying this by that. So we'll have mx times 1 over nx, like that. Right, so from here to here, went from here to there. And now, what happens, notice we'll end up with the limit as x approaches 0 of mx over nx. Right, if I multiply this by the 1, this is like over 1. What happens? The x's cancel out. And then the m and the n, remember, they're just some kind of real number. They're just some kind of constant. And the limit as x approaches 0 of a constant, just in general, the limit as x approaches a of a constant is just equal to that constant. And so from all that work, this is equal to that, m over n. Right? So just to do a quick recap of what we did, we took these two expressions, split them up into these two limits, and then we worked with each of these limits on the side. We did a bunch of work, did a bunch of change of variable, and then we ended up getting this limit to simplify to this, and then this limit simplifying to that, and then we could combine these two functions. The x's cancel out, we end up with m over n. Right, so that's how you do it just generally. So whenever you get something like this in this format and you have actual constants, it's always just going to simplify to this. So if you ended up getting something like the limit as x approaches 0 of, let's say, sine 5x over sine 6x, like that, following that same work, the m value is 5, the n value is 6, you'd end up getting 5 over 6, right? Let's say you had the limit as x approaches 0 sine 5x over just an x here. It's like a 1 in front. You'd end up getting 5 over 1, which would just be 5. Or the other way, we could have x here, and then we could have a 5 down here. This would end up being 1 over 5. Right? So you could use this result for anything whenever you end up getting constants there. You could just follow the same work. And I'm actually going to add this result to our toolbox. So we got the limit as x approaches 0 of sine mx over sine nx, and that's equal to m over n as well. Right? Just for future examples, we may run into a limit being in this format. We'll know that it's equal to m over